All right, welcome everyone to this presentation of the solutions to the KTH Challenge 2020. As you probably saw, it was quite a challenging contest, quite difficult problems, but it was impressive to see quite a lot of solutions to these difficult problems. But not all of them were solved by everyone, so let's run through. All right. So the easiest problem that people started solving very quickly was called triple texting. And here we simply got a string, which was repeated 3 times just to make sure there was no error. And then there was one of the possible characters in this string had been changed, and we had to recover the original string. So it could look something like this. Maybe we got a string saying accepted, accepted, where the middle accepted, one of the C's got changed into an X. And of course, we didn't get this color, so we only got the text string. So we had to then figure out that the original string was accepted. So one way to solve this is first we split the input into 3 equal length strings. So we split it into these three strings. And then we have to find which 2 are the same. There are many ways of doing this. We could just sort them and take the middle one. That would, if we give one of the 2 strings that are equal. Okay, so that was the easiest problem. The second problem was problem F, proofs. Here we gotten a list of assumptions and conclusions that were used in each step of a proof, and we had to check if the proof was correct. So the thing to do here is just to keep a dictionary of all of the conclusions that have already been proved. We process the input line by line, and when we're processing a line, we look up all the assumptions that are used in that line. We look them up in our dictionary. And if any of those assumptions are missing from the dictionary, if they're not valid assumptions to make because we didn't conclude them yet, then we found an error and we report this line. Otherwise, we add the conclusion of the line to the dictionary because we can use it in the future. So the time complexity of this is then big O of n times however long it takes to look up something in a dictionary, and also however long it takes to add something to the dictionary. So we just make sure to use some data structure which has fast lookup time to avoid getting a quadratic running time, and then we're fine. Okay. So that was proofs, also quite easy. So then there was a bit of a gap to the next difficulty level. The next easiest problem was probably the problem A, AI Jeopardy. Here we were given a number x, which was quite large, something around the order 10 to the 100. And we had to find the smallest n, such that smallest n and k, such that n choose k equals x. So this x is huge, so we have to be a bit clever about how we search for these numbers n and k. And the key idea is that the number n in the solution could be huge, but this number k that we're using, it cannot be very large. And the reason for this is that once we fix the value of k, the smallest possible value of n choose k is 2k choose k, because n will always be at least twice as large as k. So the smallest possible value for n choose k is going to be 2k choose k, which is roughly around the order of 2 to the 2k. So that means that we must actually have that this number k is of order logarithmic in x. It can't be too much. It can't be more than logarithmic in x, which is much more manageable than having something be linear in x, of course. So the algorithm is simply going to be, we're going to try all possible values of k, and for each of those values, we're going to do a binary search for n and see if there is any n which gives such that n choose k equals x. So the time complexity, if we do this, ends up being something like big O of log x to the 4th, It doesn't matter exactly where the 4 comes from. It's because computing the binomial coefficient takes some time when these numbers are so large. But it's not so important. The main idea is there's only going to be a small number of values of k, and if one does the computation more concretely, you can concretize this O of log x, and it turns out that the largest value of k for x up to this bound is somewhere around 168, I think, or so. One can put 200 or something to be safe. So try all the values of k between 1 and 200, or between 0 and 200, and check if any of them gives. And then do a binary search for n and check if you get the answer. Okay, so that was the third problem, AI Jeopardy. Next, we had problem D, gaggle. So the problem here was that we got a function graph. So this is a graph where you have n vertices, and every vertex has exactly one outgoing edge. So we got a graph like this, and because we got for each employee in this company, we got a number saying this employee is currently has some other employee as the mentor, and that's the outgoing edge from that person. And then we wanted to transform this graph. If you read and if one deciphered the conditions in the problem, what we really wanted to do is we want to transform this graph into a graph that was just one big cycle. And we wanted to do it in such a way that the out edges from the lower numbered vertices were preserved. So in this example, vertex 1 has an edge to vertex 3, so we would like to preserve that if possible. And if that's possible, we will then. So our second priority is to preserve the outgoing edge from vertex 2, and so on. So we're going to build this cycle basically from the ground up, where we start with nothing and we start adding edges into our graph. And for each node, we go through the nodes from 1, 2, 3 upwards. That's natural because we're trying to satisfy the requirements of the lower numbered ones first. So for each node, we're going to add the best possible outgoing edge, as long as this doesn't mess things up for us. And there are two things in which it can mess things up for us. Either we could create a vertex which has an in degree larger than 1. That would be bad because that's never going to lead to a cycle. Or we could accidentally form a cycle. And we don't want to form a cycle until we're at the very last step. At the very last step, we want to form one big cycle, but before then, we don't want any cycles. So here's what's going to happen on this example graph if we do this. So we start with vertex number 1. It wants to be connected to number 3, and that's perfectly fine. So we add that edge. Then we get to number 2. It wants to be connected to number 4, so we add that edge. It's perfectly fine also. No problem so far. Now we get to vertex number 3. Currently in the input, it had an edge to vertex number 4. So we would like to add an edge to number 4. But this would be an invalid choice because number 4 already has an incoming edge. Vertex number 4 is already taken. So vertex number 3 cannot point to number 4. Okay, so if you can't point to number 4, then it just wants to point to the lowest numbered other vertex that's possible. So the lowest numbered vertex would be vertex number 1. Okay, that would be the next best choice. But that's also going to be invalid because, as you can see, that would create a cycle between vertex 1 and 3 like this. So it's not going to be able to go to number 1. Okay, we'll try number 2, and that actually works. You can add that edge without creating any cycles or any vertices of in degree larger than 1. And then finally, the last step for vertex number 4, we just connect it to. We have built up a long path, and we just connect it, tie it up, and connect the vertex number 4 to vertex number 1 to make the cycle. So this is going to be the answer for this specific case, and this is going to be the way the algorithm builds that answer up. So in general, throughout the algorithm, what the partial solution that has been built is going to consist of a set of paths. We're going to have built some parts of the cycle. We're going to have connected some things together into longer and longer paths. So the important thing to do in order to do this quickly is to keep track of which endpoints are connected to each other, so that we can quickly check, now I'm at some vertex number 42, could I connect it to vertex 23, or would that make a cycle or not? To check that, we basically want to check whether the 23 and 42 are already like the endpoints of a path. And then, so that's checking for cycles. The other thing to check in degrees, that's much easier, because we just need to keep track of which vertices are taken and which ones are not taken. But if you do this kind of bookkeeping, you can implement this process in O of n time. You can, every time you process a vertex, you can in constant time find which is the next one possible vertex to connect it to. All right. So that's that. That's problem D, gaggle. Next, we have problem E, pitch performance, which basically asks you to compute an integral of some functions. And the two functions, one is a piecewise constant function, the other is piecewise quadratic. And the integral we want to compute is the absolute value of their differences in some range. Okay, so that's what the problem asks for. So the way we do this is we separate the calculation of this integral into intervals, so that f of x is constant and g of x is quadratic on each interval. We look at all the x coordinates where either f or g switches from one constant to another, or from one quadratic function to another quadratic function. We look at all those, and we put all those x coordinates together on the line. That in turn separates now the big interval into a lot of small intervals, and on each of these intervals, neither f nor g changes which constant function it is or which quadratic function it is. And then, so we have these intervals. We have a constant function and a quadratic function. We want to compute the integral of this absolute value of difference. So we have to do one more step. We have to subdivide these intervals a bit further. So we look at on each interval where f of x crosses g of x, where f of x goes from being larger than g to being smaller than g. So we look at where this happens. This can happen in at most 2 points, because the difference between f and g is a quadratic function, so it has at most 2 roots. So we can find those 2 roots using the formula for finding the roots of a quadratic equation. So we find those 2 roots, and this may in turn, and we then subdivide the interval further based on these crossing points, so that now we have intervals where so we have these intervals where f is constant, g is quadratic, and either f is completely above g or g is completely above f in each interval. So, and then like the absolute value, we can drop the absolute value because the f of x minus g of x doesn't change sign within the integral. The integral of the absolute value is just the same as the absolute value of the integral. So we can compute the integral without the absolute value, and that's just integrating a quadratic function. We can remember how this works from calculus, or we can look it up. There's a formula for that, and we take the absolute value of that. And then we add all of these pieces up. Right. So yeah, so we after dividing into all of these pieces, the problem boils down to integrating a quadratic function on a lot of small intervals, and we just use the standard formula for that. All right. So the next problem was problem H, winning the vote. So the way to think about this problem, I'm formulating it here slightly differently than in the statement, but the way to think about it is that we get a sequence of 1s and 2s, and then we get some positions where we are counting who is in the lead of the 1s and the 2s. So here there's a sequence of 1s and 2s, and there are 3 arrows pointing. There are 2 arrows pointing to before the first 2, 1 arrow pointing to after the last 2. And this corresponds to sample input number 3. So in the sample input, there were zeros injected into this sequence, indicating where these counts were happening. But here, instead of, I took those zeros out and instead drew arrows pointing to where they were previously located. So, and then a count gives either +1 points, 0 points, or -1 points, depending on if our party is in the lead at this point, or if there's a tie, or if the other party is in the lead. And then we want to figure out, like, how do we have to move these counters so that the total score, our total score, ends up being positive. That's what's the minimum distance these counters need to be moved. So let's see how this is solved, and let's start by pre-processing a little bit. So the first thing is, instead of having this initial array of numbers, 1s and 2s, what we really care about are these places between the numbers, these positions where we could like make a count. So let's check for each of those whether the point value is +1, 0, or -1. So at the first position, before even the first 2, the value is 0, then there's tie. Then there comes a 2, and then the value at the next position is -1, because 2 is in the lead, which we don't want. Next, there is a 1. So after that position, there's a tie again. So that point value of that position is 0. Next, there is a 1, and now 1 is in the lead, which is what we want. So the point value there is +1, and so on and so forth. So then we see that the next one has value 0, and then all the remaining ones have -1 here, because there's a lot of 2s just flowing in through in the end here. So here we see that our initial point value, like when the arrows are pointing to these things, these first 2 arrows are both gaining us 0 points, because they point to the first position. And the last arrow is getting us -1 points, because it points to the last position. So initially we have -1 points. So in order to get a positive points, we need to get at least 2 more points. We need to move these arrows so that we get 2 more points. Right. Okay. So next, we compute how far each of these arrows, how far each of these counters would have to move in order to get an additional score of +1 or +2. Since all point values are between -1, 0, or +1, the best thing we could get is an additional score of +2. So we only have to check for each of these arrows, how far do we have to move it to get +1 point or +2 points. So for instance, the first arrow, it already has 0 points. And in order to get like another point, we would have to move it 3 steps over to the +1. So it would cost us 3 to increase that arrow's score by 1. And the other one points to the same place, so it does the same thing. And since it has value 0 already, there's no way of increasing its score by 2. There's no way of moving it so that it has a +2 score. +1 is the max score for any arrow. And then this other arrow, it's pretty far back, so it's gonna have to move 4 steps even to get a score of 0. But then to get a score of 1, like an increase of 2, it's gonna end up costing only 5 steps. It's gonna have to move only 5 steps. Right. Okay, so for each of the arrows, each of the counters, we compute these 2 costs. How much would it cost me to increase its score by 1? How much would it cost me to increase its score by 2? This is like a simple scan through the array to figure these numbers out. Okay, now comes the last step, which is that we want to find the cheapest way of getting the increase we needed, and we used to do this using dynamic programming. So basically, we're going to have a state which says, what's the minimum cost to get a total score increase of some value x using only the first I counters? So then we can, for each counter, there are 3 choices. Either we keep it as it is, cost 0, or we increase the cost by 1. We know how much that costs, or we increase the cost by 2. We know how much that costs. So this leads to a simple recurrence using this form that one can use dynamic programming on. It's very similar to how one would solve the knapsack problem using dynamic programming. So the time complexity of this is then big O of number of counters times number of voters which is so it's basically n squared. It could be n over 2 counters and n over 2 voters, for instance, and then so this is basically n squared. So, okay, so that's how one can solve this. And maybe a bonus challenge, if you found this problem too easy, is that there is actually also a greedy strategy to do this last step. Instead of using the dynamic programming, there is actually a greedy strategy one can find, which gives an n log n solution. But we figured the problem set was already hard enough, so we were happy for you to come up with the n squared solution, and we didn't want to require this n log n solution. And it's surprisingly tricky. There are many ways to get this greedy strategy wrong, so that would have made this problem a lot harder, in my opinion. Okay, that was winning the vote. And so that was 6 problems done. Now we're down to the last 2 problems, the most difficult problems, both of which were unsolved before the scoreboard froze at the 3-hour mark. So the first of these was friendly fire. And here we had to find a path from the origin, represented by this little dot here, and it had to avoid some lines that were given in the input. And these lines that were given were all horizontal lines, so they were parallel to the x-axis. And the path that we had to find was each step, it always moved upwards, but it was allowed to make it was allowed to either go straight upwards or diagonally left or diagonally right. All right, so we got these lines, and we had to find something like the blue path here. So how do we solve this? Well, the first way to think about this problem is that we think of each of these lines as think of this as a triangle instead, because each of these lines give rise to like a bad area of points, which if we go into one of these bad areas, one of these triangles, then we're not going to be able to avoid hitting the line because we're only able to go like 45 degrees left or 45 degrees right. So if we go into one of these triangles, we're not going to be able to avoid hitting the line. So we had better avoid going into these triangles. All right. So now we know some parts of the plane where we don't want to go with our path, but there are still some dangerous things. So one obvious dangerous thing is that there is this pocket between these 2 triangles that touch each other. And if we end up going there, that's also going to be a problem, because then we're going to get stuck. So then we're not going to be able to complete our path. So what happens is that when 2 triangles touch, the pocket that is formed is also bad, and in fact this entire big rectangle is bad. So the lower of these 2 rectangles gets extended to include also the other rectangle, and you get this slightly large. It gets increased to this slightly larger rectangle, and then this new bad rectangle, it in turn touches now some other triangle that was previously not part of this. So this continues. So now that rectangle grows a little bit, and we get a larger bad region. So like in the end, in this example, the final bad region is going to end up looking something like this. If we go into any of these points, then we are in big trouble, and we're not going to be able to find our way through. We're going to get stuck somewhere. But these are really the only points. If we are anywhere outside this bad region, then it should be clear just from looking at the picture that there is a way of will be a way of getting out. So this kind of reasoning, merging triangles that touch, or extending triangles when they touch, and looking at the union of the resulting thing, that's basically all of the dangerous points of this instance. Okay. So, and once we have these once we have found all of these slightly larger triangles, then we can construct the path by a sweep line algorithm going upwards. So we start at the bottom and we go upwards, and at each step we keep track of which are the currently active triangles, and we keep them sorted by x-coordinate, and then we can check. Now I'm here and I want to check. I start at the origin. I want to check, can I go just straight up? Then you check, is the point I would end up with inside one of these bad triangles or not? If it's not, well, then I'll just go there. And if it is, I'll have to try one of the other two possible turns, either going diagonally left or diagonally right. So by this kind of approach, if we have all of these extended rectangles, this kind of sweep line algorithm will enable us to find the path in n log n time. All right. So then, we also have to actually figure out how to find these rectangles to start with. This was basically the second half of the problem. Once we have these triangles, how do we construct the path? Okay, but how do we find the triangles? Well, this is something that can also be done by a very similar sweep line, but in the other direction. So for that, we basically sweep downwards instead. So we start at the top, and again, we keep a set of active triangles. And whenever we add a new triangle, we check if it's touching a currently active triangle. And if that happens, we're going to do this extension that we saw before. That the triangle is going to be extended to a larger one. And then it's convenient to also think of this, the previous triangle that it got extended into. It's convenient to think of that triangle now as being cut off, so that it's not even part anymore. Because it's a bit annoying when you have a set of active triangles if they overlap each other. That makes a lot of extra details and possibility for errors, and it makes things much more messy. So it's nice to as soon as you cut off a triangle by extending, because you extended another triangle into it like this, you just remove it from which are the active ones. But so there's a lot of details to this, but in the end, one gets an n log n solution, which is conceptually simpler than it is to code in practice, but it's not too bad. And it's also possible to solve this with an n times square root of n time solution. We were pretty generous with the time limit here. All right, so that was friendly fire. Now we are at the very last problem, bling. So the problem here was to find an optimal way of making money from fruits in some game that was not called Animal Crossing, and we are not affiliated with Animal Crossing. Okay, so how does this work? It's very tempting to try to do something greedy, because the problem almost seems greedy, and in fact, the way it was originally intended was for it to be a simple greedy problem. But things don't always turn out as intended in this world. So the main difficulty in this problem is that most of the time we want to plant fruits into trees, because this yields many more fruits, and then things grow exponentially, and that's just good. Then we get lots of money in the end. However, sometimes instead of planting a fruit, we would like to. It could be better to sell off a few of them, just to make sure that we have enough money to be able to afford an exotic fruit. There was this more valuable type of fruit. Just to be able to ensure that we have enough money to buy one of those in the next few days, each of the next few days, maybe. So we might want to save money to buy an exotic fruit today. We might want to save money to buy for buying an exotic fruit tomorrow, and we might want to save money for buying an exotic fruit in 2 days. But there's never any point to save money to buy an exotic fruit in 3 days, because if we save money for something we're going to buy in 3 days, then it would have been better to just plant that fruit, and then we have more fruits that we could sell for more money in 3 days. So if we're not going to use the money in 3 days, we should might as well plant it instead. Okay, so that's the main difficulty, and this difficulty makes a greedy approach very likely to fail. We are not aware of any greedy approach that works. I'm not going to claim that there is none, but we don't know any greedy strategy that would work for this problem. All right, so then, like as a general philosophy in life, when faced with a problem where greedy fails, we always look to dynamic programming instead for hope, and maybe this will save us. So an issue with this is that we cannot use like the entire state of the farm as our dynamic programming state, because the number of trees and so on will grow exponentially. So we cannot just have a dynamic programming state saying, well, I had so many fruits, so much money, so many trees for each of the 3 different cycles, so many exotic trees, so many exotic fruits, because these numbers will grow exponentially, and you will basically never get back to the same state. It's kind of natural. Your farm will grow. Your resources will grow. You're never going to get back to any state you were in before. All right, so there will be too many states. But the solution to this is that when any of these parameters that are part of your state has become large enough, we don't actually care about its exact value anymore. So we can truncate this quite heftily. For instance, if I have 12 fruits, then that's going to be enough to buy, like if I save those 12 fruits, that's going to be enough to buy exotic fruits in all of the next 3 days, like today, tomorrow, and the day after tomorrow. And like I said before, it's never worth it to save up for anything beyond like that 3-day horizon. So I don't really care. Once I have more than 12 fruits, I don't really care how many fruits there are. So our dynamic programming state is only going to need to keep 13 possible values for how many fruits we have. Like either we have 0, 1, 2, and so on up to 11 fruits, or we have 12 or more fruits. We bundle like 12, 13, 14, 15, and so on. We bundle that number of fruits into just one state saying, well, it's at least 12. We don't care exactly how many there are. So and then we carefully look at all the other parameters and think how many, at what point does the exact number become irrelevant for this parameter? And we think this through. And eventually one ends up with some dynamic programming state which has, it's fewer than 10 to the 6 different possibilities. So just 1 million different states or so. It's even smaller. It's something like maybe 500,000 in my solution. And it differs a bit depending on how one does it. So that's not a lot of states, and for each state there's only a small constant number of options. Like you can choose how many of the fruits am I going to sell, how many of my exotic fruits am I going to sell instead of planting, and there's not going to be a very small number of options. So this then results in a fast solution. And there's a large span of possible amounts of pruning and optimization one can do on the state to make things faster or slower. We had a pretty wide span of running times from like 0.2 seconds up to 3 seconds. So you needed to do some optimization of the state, but you didn't need to do the most possible optimization. You didn't need like a super optimized algorithm for this. And this is also a problem where we had lots of incorrect attempts along the way. I think my solution was wrong 2 times before I finally got the correct one, because it's easy to make some simplifying, when you're doing the pruning, it's easy to make some simplifying assumption like, yeah, an optimal solution is always going to make like behave like in this greedy way for this parameter, and it turns out that many such assumptions are surprisingly wrong. So it's so that's this is a difficult problem both in terms of getting it right and getting it fast enough. Definitely one of the harder problems. Okay, so now comes the moment you have all been waiting for, the result revelation. So let me see what things look like here, if we can find. Yes. Okay, let me switch screen share to start with. Okay, so here is what the scoreboard looked like at the 4-hour mark. So let's see. We had Joachim and Morten sitting at 6 problems solved, Fredrik and Alexander at 5, and then quite a lot of people sitting at 4. But quite a few submissions happened during this last hour, and so we're now going to see exactly what happened. Then I have to go over here. All right, so and maybe this is not as exciting as it should be, because one can already, if one does the math, you can already see that nobody can actually beat Joachim, so it seems he's guaranteed to win. It will be interesting to see if he manages to solve C, though. And nobody is also going to be able to beat Morten for the second place, so he's gonna be in second place. For third place, it's a bit more exciting because there are a number of people that could jump up to 6 problems solved. Fredrik could jump up to 6. Alexander could jump up to 6. And Mons, down on 8th place, has 2 problems that he worked on in the last hour, and he could also jump up to 6. So all of these could end up in third place. And then, of course, for fourth and so on place, it's even more uncertain. Right, so now I'm going to unfreeze the scoreboard. Okay, so let's see what happened. Here are the final results. We see that this third place, Fredrik did get his 6th, and nobody else did, so Fredrik gets the 6th place. And for the first place, Joachim really showed who is the boss by solving C and getting a 7th problem, one more than everyone else. Very well done. Congratulations to Joachim. Good work. And all right, that actually finishes this solution and the result presentation for KTH Challenge 2020. Thank you for watching, and I hope you had fun with the contest.